DFT. What is the meaning of these equations? How these equations actually work? We discuss it in detail. Then we discussed how the x-axis of DFT can be represented in terms of three frequency variables, including capital F in Hertz unit, Fd in cycles per sample, and omega d in gradient per sample. And we also discussed the meaning of frequency resolution and its dependency on Fs and N. So we also discussed the significance of Fs and N in setting the desired frequency resolution of the DFT output. And we also discussed some numerical example on DFT. And finally, we discussed some important properties of DFT, which are the periodicity property and conjugate symmetry property. The first property, which is about periodicity, states that every DFT output will repeat after every n number of samples, where n represents the length of DFT. And in other words, we can also state this statement like every DFT output will repeat after every Fs hertz, because Fs will be equivalent to n when we represent our x-axis in terms of hertz frequency. The second property is conjugate symmetry property, which states that if the given sequence is a real valued sequence, then its spectrum will be a double-sided spectrum. So in the first half of the spectrum, which will be from 0 to Fs by 2, we will get the information of unique harmonic components. While in the second half, which will be from Fs by 2 to Fs, we'll get the mirror image or the symmetrical version of the harmonics present in the first half. So this symmetry of DFT output will be offered around Fs by 2. And why we are calling this property as the conjugate symmetry property? Because the harmonic components present in the second half will be the complex conjugates of the positive harmonic components. That's why the word conjugate is being used here. Now let's come to the today's lecture objectives. In this lecture, we will represent n-point DFT equation in the form of matrices, because matrix math is much easier to compute than solving DFT equation in a standard format. And the same topic can also be taken as the linear transformation. And I hope all of you are already familiar with this terminology of linear transformation, which is covered in linear algebra course. Any transformation is said to be linear if it can be represented as a matrix vector product. So we will see, are we able to represent the DFT equation in the form of matrix vector product or not? If yes, then DFT, which is a kind of transformation from time domain to frequency domain, will be considered as the linear transformation. So this is an analysis equation of DFT, which tells us the contribution of n number of frequency ingredients present in our x of n, while synthesis equation combines n number of frequency ingredients in order to make x of n. So our objective is to represent both analysis and synthesis equation in the form of matrices. So let's start with an analysis equation. How we can convert this equation in the form of matrices, let's see. This is an analysis equation of n-point DFT, and in order to convert this equation in the form of matrices, firstly we will check how many equations we will get after expanding this summation. And as we already know, the value of small n and the value of small k will go from 0 to n minus 1, because the length of small n and small k is capital N. So what we can do in order to get a set of equations, we can simply substitute the value of n from 0 to n minus 1. So let's check the first equation. When we will expand this summation, or when we will put the value of small n equal to 0 to n minus 1, we will get n number of terms. On substituting the value of small n is equal to 0 in this equation, we will get x of 0 into exponential minus j 2 pi k into 0 divided by capital N plus x of 1 into exponential minus j 2 pi k into 1 divided by capital N, and so on. Here you can see we have just substituted the value of small n from 0 to n minus 1, which is indicated by the green color, while we have not substituted the value of small k at this stage. Now this is an endpoint DFT equation in terms of k variable. Now we are going to put the value of k from 0 to n minus 1 in order to get n number of frequency domain coefficients. So on substituting k is equal to 0 in this equation, we will get the DC coefficient value. So capital X of 0 will be the equation of DC coefficient, while on substituting the value of k is equal to 1 in this equation, we will get the contribution of fundamental harmonic. So let's start with the DC coefficient value. We have just replaced k by 0. You can check it. Similarly, in x of 1, and for the contribution of fundamental harmonic, we have replaced k by 1. Similarly, for the second harmonic, we have to replace k by 2. And for the nth harmonic, which will be the last component, whose index is n minus 1, because our calculations were started from the 0 index. So this was the first sample, this was the second sample, this was the third sample. So definitely the nth sample will be at n minus 1 index. So for the nth harmonic, we can simply replace k by n minus 1. So this is the set of n number of equations, and every equation contains n number of terms. This is the first term, this is the second term, third term, and so on. The final term, whose index is n minus 1 for small x of n, will be the last term of each equation. So these are n number of equations, and I hope you can easily represent these n number of equations in terms of matrices. So let's see in the next slide how we can represent these n number of equations in the form of matrices. So this is how we can represent those n number of equations in the form of matrices. On the left hand side, there is a one-dimensional matrix which is also called a vector, and it contains n number of frequency domain coefficients. So the DFT output values or the DFT output coefficients will be stored in this one-dimensional vector, or you can say it contains n number of harmonics. Now, how these n number of harmonics will be calculated? It is just a product of two matrices. Out of those two matrices, the first matrix is a one-dimensional matrix, which is also called a vector, and it contains n samples of a time domain sequence, which is going to be multiplied with this square matrix, whose rows and columns are equal due to an equal length of both small n and small k. So this square matrix simply contains discrete complex exponentials, or in other words, it simply contains discrete sines and cosine waves. And here we are doing the same thing. We are multiplying these discrete complex exponentials with a time domain sequence in order to check the contribution of these discrete complex exponentials in our x of n. So to calculate DC coefficient, we are multiplying the first row of this matrix with a time domain sequence. To find the contribution of fundamental harmonic, we are going to multiply a time domain sequence with the discrete complex exponential whose frequency is 1 cycle over n samples. So to calculate a single frequency domain coefficient value, a single row of a matrix will be multiplied with the whole time domain sequence. Or in other words, to calculate a single frequency domain coefficient value, all the n samples of time domain sequence will be utilized, and this procedure will be repeated n times for the calculation of n harmonics. Now, if you observe this square matrix carefully, you will find one factor as a common factor, which is exponential minus j 2 pi over n. So this factor is common in all the entries of this matrix. So now what we are going to do here, instead of writing exponential minus j 2 pi over n every time, we are going to assign a simplified notation to this factor, which is simply w with n in its subscript, or it's simply called wn. So mathematically wn is equivalent to exponential minus j 2 pi over n. It is just a step towards simplification, nothing else. So in the next slide, this exponential minus j 2 pi over n, which is written with a black color, will be replaced by wn. But here we are observing two variables in the exponent of this exponential function as well, which are k and n. So how we can introduce both k and n in this wn notation? It will be written in its superscript. So wn, this capital N is in its subscript, and both k and n will be written as the superscript of this wn factor. And please notice one thing, this k into n is in the superscript of wn factor. It is not, you should not read this factor as n, capital N raised to power kn. It is wrong. Basically this k into n is written in the superscript of wn factor, and anything or any number written in the superscript notation of this wn factor will become the power of this wn factor, which was mathematically equal to exponential minus j 2 pi over n. So if we are going to write k into n in the superscript of this wn factor, then this k into n product will become the power of this factor, and on multiplying these two powers we can simply write exponential minus j 2 pi k into small n divided by capital N. So mathematically wnkn is equivalent to exponential minus j 2 pi kn divided by capital N. So this square matrix will be called a W matrix, which is equal to this one, and this matrix can be called as the transformation matrix, because this matrix is actually transforming our time domain sequence into a frequency domain vector. That's why we are calling this matrix as a transformation matrix. And the important thing about this transformation matrix is it is symmetric, which we will prove in later slides. So let's see how we can do it. So